Okay, my friends, let's just jump right into it because I'm going to make some claims that are going to be hard to dispute. I claim that the nucleus is made of little particles, and each one of them is these two particles, the red glowy one and the black bomber, the W and Z boson. That's all that exists. That's all that exists in the universe. And just glob them together in different ways, they make everything. These two together are what's called a gluon. We're going to go to this right now. Back to back, two gluons make a photon. You see how I made a little tiny red one, a big red one? That's because the glowy one can get big and it can get small. The black never changes. The black never changes the Z boson. This one is pushy. It's got a field. It pushes everybody away. This one sucks everybody in. The black can get right on top of the black, no problem. The black will always attract the white or green or blue or whatever color it is. But the black is strictly gravity, and it will never radiate, it will never emit, it will only attract. That's gravity, it's dark matter, it's the muon, it's the Z boson. Now I'm going to show you this, what they have to say about this. All the rest of this is nothing more than variations of these two particles in different states. Okay, my proton is like this, and all molecules are like this in the core, and every one of these little dots is a dipole electron. Now, they did a little Big Bang experiment trying to figure out the basic particles of the universe. Now, as you know, or will know, this is my model of the atomic model. All there exists is these two particles, the black and the white, which is a muon neutrino, electron neutrino. Add them together, they make an electron. Two electrons together make a photon. You keep adding the particles more and more and more, and you get molecules, atoms, all that stuff. Now, this is the Higgs field diagram of nuclear physics now. It's a new sort of thing. Well, let me tell you something. The Higgs only happens when the W and Z boson come back together. These two particles are glued together. That's the strong force. These two are glued together. They call them a gluon. You see the red and the black? It's a gluon. We separated those. All these other things, all this other stuff is nothing more than these two particles in different states. That's the photon. That's where they're in a gluon, two of them together. The photon is two gluons together. All the rest is just particles of the same nature in different states of excitation, basically. All right, don't forget, the only two particles that exist are these two. That's it. One of them is a glowy one. It could be red, blue, green, whatever. This is always the same exact particle. It's always a big black ball. That's all it is. It never will change. It's a hard elementary particle. I don't think you can break these apart. It doesn't appear to be. And the gluon is nothing more than the glowy one attached to the black one. That's what a gluon is. You take two of these and put them back to back, so you have four. That's a photon. And then all the rest is just variations. Now let's look at what they have to say and what they're all perplexed about. All right, let's start here. It says, the interaction of energy, matter, and the strong nuclear force. That's the one I'm talking about, the gluon. In the ultra-hot experiments conducted at the Heavy Ion Collider, was thought to be well understood. That's what they thought. However, a detailed investigation revealed the physicists are missing something in their model of how the universe works. A recent paper detailing the findings appeared in the journal Physical Review Letters, and it was not well received. All right, here's the real issue. They make all these guesses, and then they say this is a law. Now it becomes a law. And here's this guy, Stephen Manley, apparently, who was doing this research. He says, they said, this can't be true. You're violating boost invariance. But we've gone over our results for more than a year, and it checks out. This is what he said. And this is what happens, and they just reject it and walk away. Now, he's from, or they're in the midst of these top-end people, so he may get somebody to look at it close. All right, this is very, very simple. Quark-gluon plasma is just a bunch of particles buzzing around. Quarks, they say, are these particles. So that's the quark, and then the gluons are these particles, which this is a Feynman diagram. They don't even know what these are. These are, the gluons are the little ones I showed you, the W and Z bosons. That's what creates, the gluon comes in and creates a W and a Z boson. All right, we're talking about a quark-gluon plasma. It's a quark-gluon plasma soup. It's just a soup of these particles together. And so what particles are we talking about? These are quarks. They say a quark is a fundamentally elemental particle with these three little bits inside of it. Well, I disagree with that. I say that everything is made out of all dipole electrons. Now, then they say, what is a gluon? Well, a gluon is a dipole electron. It is not. This is a Feynman diagram saying how they see this interact. They just don't understand what it is. It's made of that white and black particle together, and that's what a gluon is, as I showed you, I think, pretty clearly. So we know now quark-gluon plasma is just those things in a soup. You know, at first I was against this quark-gluon plasma, but now I believe that they are correct. The gluons are simply the two particles together. Now, sometimes they can be red, blue, green, they can be all, it depends on how hard they're hitting the next item. Are they hitting just like that? Then they'd be blue. Are they hitting like this and bouncing off? They'd be green. Are they just cruising past each other? They'd be red. This is the interaction. The only time you can see any energy level whatsoever, there has to be some interaction. There's nothing that is energy just sitting there. It doesn't have any energy. It has to be interacting, pushing or shoving or drawing another particle to it. There has to be some interaction. This is a collision. Say these both were hitting each other. This is a big proton. In my world, that's huge. We don't have this. We have cohesive light. We have either it's red or it's blue or it's green. There's no big bits like this, but they could have this, absolutely, because they have a big ball like that. We have this. So we're only going to get one certain color. They have this smashing into another one. So in other words, let's say that this particular one right here hits exactly head on to that one right there. You're going to get blue. The other one here hits green, just slides off, you're going to get green. So I will accept this now, the plasma gluon, a gluon quark plasma. But we don't have that. We have only one frequency of light, because we have only one interaction. All right, let's take the next little tidbit. It says that this plasma is a very brief state where the temperature is tens of thousands of times higher than the cores of the hottest stars. Well, I don't know about that, but I can tell you this. It is brief because they're hitting head on. They're just going bam, case closed. We are squirting ours out, and we can go right onto a substrate. And I'm telling you, it looks to me like we got some burning little particles coming out of there. We just got the white ones all by themselves. And if we can get the white ones all by themselves, I think we got a winner. And we can. And I can show you why I feel we got a winner by separating the white from the black. Let me show you. Okay. As I said, all the white particles will always surround the dark matter. Literally surround it. And all the blacks will go to the center. So we never have seen the black because it's in the center of everything we've ever looked at. All we get is a bounce back. But if we were able to take this white completely off, that's what we would find inside of every molecule, inside of every proton. This is what matter is made out of, is white surrounding black. So, what if we could get rid of that white, which is the glowy, burny part, the little bitty bits, and get it away from the dark matter? It would go out first because it's always going to surround the dark. So if that exploded, the white would go out first. And that's the burny stuff, and it has no mass. I've shown this a lot of times. Watch what happens in this nuclear bomb blast. The first thing will happen, and this is atom central. The first thing that will happen, you'll see a huge glow and the house will just vaporize. I'm going to put this on 25% so that it goes real slow. And I'll turn off the sound so we're going to go like, okay, here we go. Now, so atom central, here goes. I'll bet you I'm going to get a commercial. Hold on one second. All right, let's see what we got here. The first thing that'll happen is you just see a brilliant white glow. And the next thing is everything combustible will just fume. Watch, the metal doesn't. Okay, but the wires in here and everything that's combustible burn, it's gone. That's because of those white, now the black particles come. The first one were the white particles. All right, and now the stuff comes back to fill the void after the explosion. Now, let's take another look at something here. All right, remember this. The nuclear explosion goes off, and because the white is always on the outside, always, at 10,000 times always, and inside is the black. But with a nuclear bomb, something happens that we've never seen before. We crush everything in, and then it comes out, and all the white comes first. So here's white all over this thing. There's no movement. Nobody went anywhere. That didn't burn because it's metal. It's not. The electrons didn't get absorbed the same way they get absorbed in flammable things. Flammable means if you put enough heat on it, it's going to burst into flames. Metal is not normally considered flammable. But the wires, even the wires, the telephone poles, everything, the big metal chunks will not burn. But these burn. Because all of these electrons are trying to take the place of the electrons that are already in that material. And they say, no, you can't come in. They say, oh yes, we're coming in. And it's push to shove makes glow, glow makes heat, heat makes burn, burn makes fume, fume makes just combustion. No movement. I find it very hard to understand, to be perfectly honest with you, because we know they had to come from the explosion. So they're moving. There's no question they're moving. But they have no mass. And that to me is just very, very difficult to explain. Now, the next thing that happens, as we know, the black particles are right behind them and going, because they were on the inside. Now when they hit, watch, I mean, it's all over. Instantaneously, everything goes. There's no more burning. But now everything gets pushed this way. You see it? Look at how hard that's hitting. Now, I would like to know what the temperature is in here when this hits, because I know the first one was off the charts hot. This, I think, is off the charts cold. And then it turns around and gets pulled back. Now, is it getting pulled back to the dark matter? It's still back there? Or just because there's a void, I can't say? Or is it? It's probably both. Okay, so these are the particles that come streaming out of this hot plasma soup, where the quarks and the gluons and all that form their plasma. And here it is right here. And there it is. Right here, it's both the black and the white particles still here. The black, the only reason you can see the black is because it obscures the white. Otherwise, you never see the black. It would always be inside of something. We separated them. The black is sitting on top of the white now. That's why you can see it. Same thing here. Otherwise, you'd never see it. You'd never see the black. Now, we created the sterile muon. We created electron showers here. Did we create fusion and fission? Absolutely. That's fission. Those two are attached together. This is fusion. They're coming back together. And here's where they were attached together in the strong force. This is the strong force. And these are the two particles that they see at Fermilab and CERN, and they know they're the tiniest particles they can see. And this one they say has no mass. I agree with that, virtually none. This one has all the mass and no burn. This one has all the burn and no mass. As far as I can tell, that's what I'm looking at. Now check this out. This shows it all in one shot pretty good. This is just the light starting to accelerate. Here's where it really accelerates and it splits. You saw the black and the white. It comes back together. So the white has to come back to the black. The white can't exist on its own for more than like an instant. This is light. So this is like about that far away from the Venturi. It's right next to it. What is coming out of here is these Higgs fields are coming at us. So this would be like we're looking right down into the laser as it's coming through the Venturi. These are the fields that are coming right at us. These fields coming right out of the Venturi. And that's what they are right here. And guess what you're looking at there? Think about this for a second, my friend. This right here is the tip of one of these waves. Those waves are like a funnel going back. It's like a spring going back. The tip hits first. See it? It's like a leading edge. It's absorbing black and turning back into just a normal particle, a normal electron. And all of these are trying to catch up. Some of them have picked up a black, but most of them are still in their complete white phase, and they're starting to transition. You see them? And then all of a sudden, so the black, I got a feeling the black, it's melding in back together, and the black always goes to the center. It just goes right to the center. And that's what I'm saying. Even on the electrons, the black goes to the center. As far as I can tell. If you see it any different, I'd like to know why. All right, this is where it really got interesting. I always knew that they were dipoles, but I could never really put my fingers on everything. Then, with our light experiments, I could see the two particles separating, the black and the white. I said, holy smokes, we created monopoles. That's just insane. Because they should be glued together with that strong force. Now, the reason we were able to do that is because everything is made of just what you see in here. There's a black center and all the white particles surround it, which makes it a molecule, or it makes it an atom, or even, to me, it looks like it makes it an electron, because we saw the black with the white surrounding it as the Higgs fields came in. This is what's happening. This is it right here. That's always going to be in the center. What we just saw is the Higgs field, as it comes at us, the white is smashing into the black and going to absorb it and surround it. That's what I'm seeing. Maybe you see something different. Anyway, this was out in space, and the reason they could see the exact same thing that I'm talking about right there. The black goes to the center, always surrounded by the white. You never see the black. All right, I got to be perfectly honest with you. I'm not involved in this research whatsoever, and I got to be honest with you, I'm not sure what they're talking about without doing a little more research into it. However, I do understand that there is something fundamentally wrong. It says it may be that we have an actual clue here that something fundamental is different, something we just don't understand. That's the dipole nature. This is Stephen Manley. Now, when we first presented this at a conference at Stony Brook, the audience couldn't believe it. They said, this can't be, you're violating the boost invariance law. We've gone over the results for more than a year, and it checks out, is what this guy Manley says. Now, let me just see if I can illuminate anything more. Hold on. All right, it appears what they're talking about is all of the different debris rather than just the impact zone. And that's all they've ever, they talk about being the sweet spot. Let me show you. Because this is when they hit head on, and then they just splash everything everywhere. They make the Higgs fields, no question, but that's because the particles just spin. See, I fully understand already the particle nature, the acceleration nature, the stacking up nature, the neutrino nature, the splitting nature, creating fission, the fusion, and I understand right here there should be raw energy. If this is anything like it is when I hit that house, we're golden, and we should be able to harvest that. All right, think about it this way. These are the particles. We know they were black and white. We know they were attached together as gluons, a strong force, and two of them together made the photons, and they showed up here, and then they separated here. Now, this is the reason why. The white is gushy and glowy, and it can squish right down through that tiny little slot. The blacks are just too big. This is obviously an exaggeration, but if we look at them very closely, we can see them, and they don't get through. They have to go around. And then they reattach right over here where I showed you the white particles are actually red, wrapping right around the black to reabsorb them to become normal particles again. I think this is pretty convincing. All right, now this is a really tight shot. This is raw electrons, raw white as far as I can tell. And these are the black ones that are going around and reattaching right back here. And I believe I've shown that pretty clearly. And of course this is where the Venturi is right here. Little tiny slit. The white ones squeak through, the black ones are just too big. Just too big. Okay, my friends, this is one of the most exciting shots I have. Right there is the Venturi. We're looking down into the Venturi. The particles are coming out at us. We are in the middle of the white field. Remember there was a big white spot with just nothing but white? That's here. You see these little tiny spritzes of that? These are the white spritzes. You see them? And that's all they are is white. And then as soon as they hit a certain area, they start to reincorporate and create these spinning fields. Now, why is this so interesting? This is all red laser coming through here. Red, coherent, red laser. Now, what happened here? That looks like purple, and that looks like almost orange. And look at how these are elongated. Look at that. That's totally different than on any of the rest of them. Look at that. Just think about it. Just take your time. You can stop and just think for a while. But you see, every one of those is a zip, 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 little white particle. Now, what's going on here? What the hell is going on there? It's the only one I've ever seen like that. I believe this is spinning backwards. And normally they spin to the right and they throw the particle out. This, well, they throw the field outwardly. This, I think, is gathering a field into itself. And I believe the next shot I'm going to show you is this particle as it interacts with a standard Higgs field and creates the craziest thing I've ever seen. But I am showing you things that are very, very difficult to dismiss. And the Higgs fields, does show you this is exactly what they look like. And I'm showing you the particle that does exactly what they say. One's heavy, one isn't. One burns, one doesn't. I don't see any reason to totally discount this and just say the guy's crazy. Let's not even bother looking. And that's what's happened for years now. All right. This is a standard Higgs field. Now this, I believe, is that white glowy particle. And it has some kind of a structure to it. Now, let's move down and see it glowing here? And it has some kind of a structure. Now, underneath is another Higgs field that appears to be interacting with this field. Somehow, something's going on here. And then this is getting twisted off of this field, I believe. These are spinning disks. Now I think one of them spinning this way and one of them spinning the other way. And what happened is this one grabbed a hold of this disk and spun it off this little piece. Because I believe one of them, like I say, they're both spinning, I believe. Nobody's ever seen anything like that, trust me. But whenever you see glow, it means something's pushing and something's shoving back. This is glowing because it's coming through the air. This is glowing because something's pushing against that. Now, whether it's pushing this way or that way, I'm not sure. But what it does is it's leaving this little tiny field like this, which, to me, I don't know what to think about that, to be perfectly honest with you. I have no idea. Absolutely none. Zero. Let me just make one more statement. I do believe it's peeling off this row right here. It's just peeling it right off by pushing against it. Or it's got to be pushing this way. So this field is spinning this way. And it's hitting this field and just grabbing and spinning this off. Normally they'd both be spinning in the same direction. This one's spinning into it, and this one's spinning that way. That's what I'm seeing, because that would account for that kind of a reaction. Normally they're going to spin sort of evenly, and you know, this is glowing because it's going forward. This is not glowing because it's going forward. It's glowing because it's being scrubbed. And it's being peeled right off of this disc. So this disc is going this way, and this disc is more powerful going this way. It grabbed a hold of that and twisted it right off and spun it right out like that. That's my approach on this one. You see this? This is exactly what they're talking about in that article. They have to be able to see these things from different perspectives. We have to look sideways from the back, or up above, from below. Remember I showed you the blue one, and then I showed you the elongated one? These two are pinching this. And it's pinching that, and it's actually forcing it to squirt. Like, see how it's elongating it? These are flatter. You see how they're nice and flat? Well, they're not flat. This is the tip that starts to concuss with the black. But this one is being crushed and exceeding it and turned blue, which means that's a much more powerful particle. This is the only time I've ever seen this either. And this one here is slowing down and, being elongated because it just squirted it right out. That's what it looks like to me. Again, this is all sort of new stuff. I mean, it's all 100% new. Now, where do you see this? You see when this stuff hits here and it starts creating these fields? Let me show you how that happens. It's stunning. By the way, you see this? This is that Samsung phone. Same one I use. I had the same one, Galaxy S3. And Rod loved it. He thought it was the best ever going. And he used the selfie side, which apparently has a lot better resolution. You can see the Samsung up there. Right there, Samsung Galaxy S3. I had the same one. I have one here. And but Rod was the guy. He knew what to do. But that was a fabulous phone. This goes back to 2014, 2015, I think, somewhere in that area. And this was all done. By 2015, everything was done. All of this stuff, that's about when we stopped. Other than I've been showing it over and over, hoping somebody would take some interest. And this is CMOS. It's what they're just saying, oh, now we're gearing up at the Large Hadron Collider to use CMOS to watch these events. Back then, they told me it was impossible. I said, no. And everybody's doing it. You're watching from muons with smartphones. And they didn't want to hear about that because they were using protons. So it was a little contentious. But anyway, at this point, we need to get this done and get this straightened out. Where do you see the interaction as well, let me show you. Look at that. That is just outrageous. This is raw white particles. Just nothing but the white ones. And here's coming in and just slamming into the atmosphere. And all of these are Higgs fields. And every one of those is a particle, is an electron shower, I guess they would call it. This is the electron showers. And they're all just spewing out. See, every time you see little white spits, it causes one of these fields. And they just take right off, spinning. Now, I showed you how complicated these fields are, but I think I understand it because I'm not looking at it just as an explosion of garbage. I'm looking at the actual event in real time. They're saying, aside from revealing that scientists are missing a piece of the physics puzzle. Hold on a second. Okay, sorry about that. Compressor kicked off. All right, now, aside from revealing that scientists are missing a piece of the physics puzzle, The findings mean that understanding these collisions fully will be much more difficult than expected. Because again, they're hitting head on, getting garbage everywhere. No longer can the physicists measure only the sweet spot where they touch and smash, where the atoms collide, where they initially collide. Now they must measure the entire length of the plasma. And I showed you that plasma stretches out for a while, effectively making what was a two-dimensional problem into a three-dimensional one. As Manley says, this dramatically increases the computing complexity of any model research tried to devise. No, I'm showing you the model. You can see it. Now, you can compute it however you want to, but I can show you the two particles, and I can show you how they react. Now, it says modeling and understanding the collisions are extremely important because the way that the plasma cools, condensing like steam, turning into water, well, they're talking about all these different things. They're talking about how it reforms. These quark-gluon plasmas behave as it does. We might gain an insight into some of the rudiments of the world we live in. Yes, exactly. Understanding all the dynamics of the collision is really critical for actually trying to get the information we want. Agreed 100%. It may be that we have an actual clue here, I'm showing the clues, that something fundamental is different, something we just don't understand. Smiling, he adds, yet. Well, I understand, and if you will speak to me, Mr. Manley, maybe we can understand it together. Okay, the unexpected results stunned the physicists. Well, they didn't stun me because my model takes into account the dipole nature of particles. Now, somebody from the particle collider people, wherever, I've been trying to contact them. I just sent it out to the people that were on announcing this big discovery of fusion the other day. I just sent it to Don Lincoln from Fermilab, sent it to everybody, and I'm hoping for some response. Now, this is my email, roger@mudfossils.com. And if you look me up in Mud Fossils, it'll talk about that I discovered that soft body tissues could turn into stone, like this goose head with its feathers and everything. And I understand the process, and I've had all DNA tests and CAT scans and everything else. And bones and lungs and hearts and livers and heads and everything else. Body parts pieces of meat, actual looking pieces like a piece of meat, like you would eat. Steak can turn into stone. And this is what they'll say, oh, the guy's an idiot, because they don't like that in the geology people, because it changes everything for them. I change everything here for the physicists, they don't like me for that. So I'm in a position where nobody will talk to me because everybody doesn't like me because I infringe on everybody's territory. I'm sorry, I want truth. If you want truth, you better start talking to people, because they will not stand up for themselves. I have really literally assaulted these people, these academics. Not a single word from them. I would be enraged if somebody talked about me the way I talk about them. And I have every right to say everything I'm saying because it's all true. All right? Somebody get a hold of me. The first person who gets a hold of me and starts to engage in reality will be the one that's looked at as a hero, because you'll be stepping out on a very, very bad, a tricky limb. You're going to be on a limb that breaks very easily, and you lose a lot of friends very quickly. But if you don't do this, you are not a scientist. That's how you get a hold of me. All right, this is one of the things they talk about, offsetting the Venturi for us. I don't know what they were offsetting for them, but all of our black particles went this way. Not a single black one went this way. This is the green. So, depending upon the way you look at it, you're going to see all black or you're going to see all white, where the red was a little different. All right, you can see all the little spritz of the red and all the red particles coming up, but the red is nowhere near as reactive as the green. All right, don't forget though, they're all the same particles. The green, red, doesn't matter. These are the ones. The black is never changes. The black is never going to change. Same size, all size fits everyone. This one here can be red, every color I believe, and the different colors determine the different spin rate basically. And the different spin rate determines the concussion value, which is the mass. Now, this again, we split them. We just split them. These are the strong force. This is what holds light together and holds electrons together. That is the strong force. And when you add a whole batch of them together, you end up with molecules and protons. And we split these apart. So we're into the most basic spot that you can be in. And we showed that the interaction changes all over the place. And it depends on which color light you're using, which intensity light, and how it hits the venturi, and all of those different things. It's very complex, absolutely, but it's easily understood. Very important statement. It's the things you weren't expecting really trying to tell you something in physics, says Stephen Manley. He sounds like a smart guy. I'd like to interact with him. He's the Associate Professor of Physics and Astronomy at the University of Rochester and co-author of the paper. The basic nature of the interactions within this hot, dense medium, or at least the manifestation of it, changes depending upon the angle you're viewing it at. Absolutely. We don't know why. I think I explained it, I hope. We've been handed some new pieces of the puzzle. We're just trying to figure out how this new picture fits together. And I am too, Professor Manley, and I'd love to interact. I really honestly would. All right, that is at the instant of combustion. Look at the size of that thing explode. Now let's come back here just a hair. I got it going at 25% speed. Let's see if we can. I'm going to keep stopping it, going and stopping, going and stopping. All right, now watch real careful. All right, so it was right about here. You know what? Let me do something here. Let me draw where that thing is. I think it doesn't change the perspective of the camera, does it? No. All right, so here's the balloon. Now let's see what happens when it explodes. Where does it go? Because he's lighting it from here. Where does that explosion move to? Oops. A balloon moved. Let's figure about right there. Wow, look. All right, now we're seeing something. He just broke the surface. Out comes the gas, igniting into the air. And just instantaneously, it's all over. And it's done now. Everybody's laughing, going crazy, and he's got a big smile. This is water vapor, and the reason that is water vapor and not smoke is that he started out with H2O2. If you see on the blackboard there, see that? He's got two H2s and O2. It ends up being two water molecules, two of the water molecules, and then the oxygen's left over. Now, the oxygens have turned into electrons, and then we heard the concussion. The concussion forces the remaining hydrogen and oxygen to fuse together into no longer gases, they turn into water molecules. Condensation, it's called, and that is as hard as condensation you're ever going to see, that explosion. Alright, this will give you an idea of the difference in the power. Look at how weak the red is compared to the green. They're both coming through the venturi at the same time, and it's like there's a pin here and on the other side there's a pin. So it's coming through this slot both at the same time. Look at how the green is way more powerful than the red. and it reconcusses way out here. You just push the red out of the way. So they're the same particle. I showed that. The red, well, let me show you so there's no question whatsoever. The green and the red are identical. They both have the same black particles attached to them, only the green is just spinning much faster than the red. But other than that, as far as I'm concerned, there's no difference whatsoever in the particle itself. It's strictly the rate of the spin which dictates the impact value. All right, I think I've shown you, but I just want to be positive. There's the two blacks, there's the two whites. That's a green photon, and it is powerful compared to the red, as I showed you. But this is the red, which is identical. There is no difference. There is no difference whatsoever. But one of them just is more powerful than the other. So the only thing I can take away from it is one's going faster than the other, or it's just spinning faster, and the spin dictates the smack that it hits. Either that or it's got to be going faster. No, it looked like it was going faster to me, but I can't say one way or the other. I can't measure the speed of light. All right, this is light coming through a glass bubble, I believe. And again, Rod did this. He didn't give me a lot of details, but I think I understand what's going on here. Each one of these is literally a photon, and they spin like hell. Now, coming through that glass bubble, it's like a curved bubble. So when they come through, they sort of hit together here and form this tube. Now you see these glower ones? This light is spinning this way. It's pinched here and there. That's when wherever you see the most glow is the most pinch. It's the most push and shove. And as it comes through here, they splay out and go flying. Now, this is a pulse laser. The only thing I can take from this is that this is the original pulse. I'm sorry, this is the second pulse. This was an original pulse ahead of this one. And we're looking at the back of those particles going that way. I'm not kidding you. And that's this. This is the back of this pulse. The pulse only lasts a certain pip, 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 so it's only a certain distance. And I think we're just about at the end of this one. It's almost completely gone through. When it does finish going through, if we were still looking at the back of it, we would see this. I believe that's the way I'm taking this. Okay, I'm going to wrap it up with this. Regardless of how you take this, we created the muon neutrinos and the muon and the electron neutrinos, and we created the stereo muons and the electron showers. And we did it the same as they did, using from the Cherenkov radiation, creating these events, because we pinched it. And by pinching it, we did the same thing as slamming it into heavy water. But we were able to control it because we have a Venturi. So right here, if we were to put our harvest plate in here to absorb this raw energy, I think we got a winner. I think we can get free energy.